Okay, students, we're on Mod 1, Topic 2, Lesson 3, page 115, if you're not already there. Okay, so now we're going to talk about reflections. Keith, remember last lesson we did translations? Now reflections. Remember we got reflections, translations, and rotations that are our isometries, also called rigid motions, and they are congruent. And remember, congruent means same size and shape. So whenever I move them, and remember that's the pre-image of the first one, it ends at an image, they better be the same size and shape when we're done. Okay, so here we go. Some review. It says reflect triangle ABC across the y-axis. So you gotta know which one the y-axis is. Remember, reflections are at 90 degrees, also called perpendicular, to the line of reflection. And the same distance away. Okay, so if we take point B here, and we go 90 degrees to the y-axis and go same distance, which is 2 away, I go 2 away in the other direction. There's B prime. A is only one distance away, so 1 away, A prime. C prime is 1, 2, 3, 4, 5, so I go 1, 2, 3, 4, 5 over here, C prime. And then go ahead and reconnect those. Okay, you've got one that simple on the DCAS, just doing that. Okay, why do people miss it? Because they don't know the difference between the x and the y-axis. It should be free points. So we got so many people that still don't know the difference between the x and the y-axis. If it's multiple choice, they'll have both those there, the x-axis and the y-axis. And so if you pick the wrong one, you blow it. It should be free point. So there's my x-axis. D is 1 away, so I go 1 away up here, 90 degrees to it. E, 90 degrees to the x-axis, go 2 away from it, E prime. And F is 1, 2, 3, 4, 5, so I go 1, 2, 3, 4, 5. F prime, and then just reconnect them. That's it. Okay. Should be very simple when you have that. All right, let's go to the next page. Perpendicular bisector theorem. Go ahead and write this in your notes. Okay, any point on the perpendicular bisector is equidistant from the endpoints of the segment. You're going to see it later in the lesson, but I'm just going to talk about it right now. So remember, we constructed in previous lessons, you constructed the perpendicular bisector. Remember, we put our pointer on one point, open it up more than halfway, drew a semicircle, turned around, put the pointer on the other end, drew that semicircle, and then we connected right through there. And then that made us perpendicular and a bisector. So that distance equal that distance. There's your perpendicular bisector. Okay, so now what does that mean? So first off, you're going to see something like that with the arcs on there without the line being drawn through it, just the arcs there, and they're going to say what was constructed here, and you have to be able to say perpendicular bisector. So what does the perpendicular bisector theorem mean? Any point on this perpendicular bisector, such as that point right there, is equidistant from the endpoints of the segment. So that distance equals that distance. We'll do one more. Let's say I pick this point right here. Same distance from that endpoint to that endpoint, same distance. That's what the perpendicular bisector theorem says. All right, now go to page 118. Okay, a reflection is a function that takes its input, which is the pre-image, the location of a point, and outputs the opposite of that location with respect to some line of reflection. A reflection is isometry. Remember we just said, we went over it. Another word for isometry, rigid motion. Got to have that down. And always congruent. Congruent symbol. And what does congruent mean? Same size and shape. Okay, you should have this memorized by now. Okay, and we already talked about a reflection line. It's 90 degrees to, we just did in our warm-ups, 90 degrees to the line and the same distance away. Okay, so vocab right there. Describe the relationship between the corresponding points of a reflection and the line of reflection. We already said it. 90 degrees to the line, 90 degrees, or you can say perpendicular to the line, and same distance away. So you reflect it over the line, the same distance as it was to the line. Okay, go to the next page. Complete each reflection using the given function. Okay, so remember we reflect, capital R stands for the reflection, over line M. There's line M right there. Remember, you can name a line. If it's a lowercase, it's got to be at one of the arrows. Otherwise, you would pick 2 points on the line. So they call it A and B. You could also call it reflection over AB, which would be line AB. Okay, they don't have any points on line, so they choose the lowercase letter. Again, making sure that you know how to name lines correctly. Of STUV, so that means this is our pre-image. That's always the pre-image. Oops, pre-image. The I goes, oops, oh, pre-image. And then it creates the image. So there's my pre-image right there. Creates the image over here. Again, 90 degrees. That's what this is right here. Like this, there's 90 degrees and the same distance. Whatever that distance is, I go the exact same distance over there. So that'd be T prime. I measure from S, perpendicular, same distance, went out, S prime. V, went out, measure that distance, 90 degrees to it, go out the exact same right over here, V prime. And then same with U to U prime. That'd been U prime right there. Okay. And there is your image, creating the image there. Here it just tells you how to read it. A reflection of points P, Q, R, and S across, I like to say over, but across line L. And it should be and perpendicular and same distance. Away. Same distance away from the line. For the corresponding points there, each corresponding point. Okay, go to the next page. Okay, it says you can identify the line of reflection between two figures. So how do I do that? The line of reflection is also called, as I wrote over here, the perpendicular bisector. So line of reflection equals the perpendicular bisector. So all you have to do is take a ruler, for example, and find the midpoint between A and A prime. That's one pair of corresponding points. And of course, to make a line, I need 2 points. So I do it again between C and C prime, find that midpoint right there, and then I just go ahead, take my ruler, and connect those. And there's your line. So that's how you can do it by freehand. If it was on the coordinate plane, I would just take those 2 points, and if I wasn't sure where it is, I take those 2 points and use the midpoint formula and come up with that midpoint. Use the midpoint formula for C and C prime, come up with that midpoint. Okay, and then connect that, and that'd be my line. The other way to do it is construct it. Remember, you used perpendicular. Put your pointer here, open up more than halfway, draw your semicircle, turn around, put the pointer on this end, same thing. Draw your perpendicular bisector. There you see perpendicular bisector. And then connect them. Okay. And here they're just showing you again how to do it. All right, go to the next page. Determine whether the figures are reflections of one another. If so, identify the line of reflection. So if it's going to be reflections of one another, again, you just take 2 corresponding points, find the midpoint. Take another 2 pair of corresponding points, find the midpoint, and connect them and draw that line and see if when I go 90 degrees to that line, it lands up same exact distance away on the other side for each of the points. If it does, that is a reflection line. If it doesn't reflect, because a reflection is only a single line. So, for example, that point matched up with that point, the midpoint would be right about there. Okay. The one to the right of it is here, and the one to the right of this one, because it's upside down, is right there. And I take its midpoint right there, and I connect them, and there'd be my line. Now, when I go 90 degrees to that line, or 90 degrees to that line, it'd be like this. Okay, and that ends up over here. That does not end up where it's supposed to be down there. So therefore, or I could have taken this one, 90 degrees to it, ends up right there. It doesn't end up down here for any of these points. Okay, so there is not a reflection line right there. I mean, it's going to take more than a single reflection to get there. Here, again, I could take those 2 points, find the midpoint about there. Take those 2 points, find the midpoint about there, connect it. Okay, and of course, when I reflect this across at 90 degrees, it puts it up here. I reflect this across at 90 degrees, it puts it up here. So it doesn't end up over here whatsoever. So a single reflection does not work for that either. Remember, you should recognize this is a translation. A translation equals 2 reflections over parallel lines is what the real definition is. 2 reflections over parallel lines. Okay, and so remember, it wanted to know if it was just a single reflection. No, it takes 2 reflections to do a translation. Okay, so this one up here is a rotation. It rotated, okay, for B there. How do you know whether 2 figures are not reflections of one another? One way to test this is orientation. Okay, orientation refers to, like, say I call this A, B, and C, and this is, let's change the color here, A prime, B prime, and C prime. So notice ABC, the orientation is clockwise, and A prime, B prime, C prime is also clockwise. So they're the same orientation. So orientation refers to clockwise versus counterclockwise. If they're the same orientation, let's write this down here. Same orientation. They can both be clockwise or both counterclockwise. It doesn't matter if they're the same orientation. Remember, so orientation can only be clockwise or counterclockwise. Then it is either a translation or rotation. And we'll look at those in another lesson. Okay, so since these have the same orientation, it's either translation or rotation. So therefore, it's not a reflection. Reflections have opposite orientations, not the same. Okay, so if one was clockwise, the other would have to be counterclockwise, opposite orientations in order for it to be a reflection. All right, go to the next page. The other way, that's how I like to talk about it. But another way is, can I get from the pre-image to the image in a single reflection line, over a single reflection line? And the only one that occurred for was A. B and C, you cannot. Okay. So can you get from the pre-image to the image with a single reflection? That's another way of saying that, if you don't want to look at the orientation. Perpendicular bisector theorem, we've already written it down. Now here's where they actually put it in here. Here's your perpendicular bisector right there. And it goes ahead and says you can prove that the endpoints of the line segment, that's points R and B in this case, remember endpoints, those are called the endpoints, there are no beginning points in math. Endpoints of a line segment, and you can't have endpoints on a line or array. On an array you have one endpoint, but endpoints plural can only occur in a segment. are equidistant from any point on the perpendicular bisector. We've already written that down, okay? And so now we're just going to look at it. So go to the next page. There's that formula, or the theorem, I mean, that we've already written down, so you shouldn't have to write it down again. Okay. Now we also have what's called an angle bisector. We have a perpendicular bisector, and we have an angle bisector. Both of these are on the DCAS. Okay, so how do you construct an angle bisector again? Is I put my pointer on Q, go out a certain distance, draw an arc. That gives me 2 points there and there that are on right there. Then I put the pointer on one of those, open it up more than halfway. So it's there, draw my arc. Turn around, put the pointer on the other one, keep that same distance on, don't change the length of that from the pointer to the pencil. Don't open or close it. Same distance. Draw its other arc, and then I can connect it from Q through that point of intersection right there, and that creates an angle bisector, which means it splits that angle in half. Bisect 2 sectors, so splits in half. Whatever you think that. Go ahead and go to the next page. A counterexample vocab word is a specific example, just one. Notice it says counterexample, not examples, singular. Is a specific example that shows a general statement is not true. Okay. So anything, draw examples or counterexamples to justify your reasoning. Okay, she said that you can always map one congruent line segment onto the other using at most 2 reflections. So this is not correct because there's a three reflections. It's called a glide reflection. 3 reflections, which is a single reflection followed by a translation. And remember, a translation is 2 reflections over parallel lines. So that took 1 reflection there, plus a translation was 2, for a total of 3 reflections. And that one is called a glide reflection. This book doesn't talk about that. So I'm just having to tell you that. But that would be an example, because she's saying you can get from one to the other with only at most 2, meaning 1 or 2. No, if I do a glide reflection, it would take 3. Okay, so an example of that would be, let's say I take this triangle right here, okay, and I have a line of reflection right there, reflect across that line. So it goes like this, here, okay. Let's just say it looked good, it's the same size and shape right there. So that was 1 reflection, and then if I slid this up a little ways, say right there, okay, so that's a translation right there. That was a reflection right there, so that's a total of 3. So I could not go from here, that would have been A prime, B prime, and C prime, oops, single prime, to now this becomes A double prime, B double prime, and C double prime. I cannot go from ABC to A prime, B, A double prime, B double prime, C double prime in 2 reflections. It took 3. It took a single reflection, and then what this is, you really have 2 reflections over parallel lines. Okay, that moves it, slides it up. So that took a total of 3 reflections. So that'd be an example, also called the counterexample. All I need is 1 to show how that would not work. Okay, so now you got to see what a glide reflection is as well. All right, triangle GHJ is a reflection of triangle MNP. So reflection singular, remember that means it's 90 degrees to the line the same distance away. Describe the locations of the midpoints of GM. So midpoint of GM, HN, and JP right there. I take those midpoints that I was showing you before, connect it, and there's your reflection line. Okay, go to the next page now. Describe and sketch the sequence of translations and reflections that show that the two figures in each pair are congruent. Remember, congruent means same size and shape in all rigid motions and isometries are congruent. So our three types, if it's two reflections, it's translation or rotation. If it's a single reflection, it's or a glider reflection. Remember, there's the three I just showed you, the glider reflection. Single reflection is just one reflection. Glider reflection is three. Okay, these have the same orientation. Same orientation. We talked about this before for both the translation or rotation. And single reflection and glider reflection have opposite orientations. Okay, so by checking their orientation, I can wipe out two of them. Okay, I can wipe out either reflection or glider reflection, or I could wipe out the translation or rotation. So let's see. ABC is clockwise, DEF is clockwise. Okay, so that means it's either a translation, which means that does it look just like this over here, just shifted over here? No, it doesn't. So since it's not a translation, it has to be a rotation. Okay, since it has the same orientation, it's either a translation, which means it just slid, it doesn't rotate at all, or it's a rotation. Well, obviously this rotated like this. Okay, this rotated like this. This rotated like this. So that's a rotation. And just so you know, since it went clockwise, that's negative degrees. Don't forget. Remember, clockwise is negative degrees. Counterclockwise is positive degrees. All right, next page. Describe the sequence of translation to reflection, which maps the pre-image triangle PQR onto the triangle ABC. So this is actually a DCAS question right here. There'll be something just like this in the DCAS. It has been. So it tells me P matches up with A. So PQR to ABC. Okay, so what is this? Counterclockwise, ABC is clockwise, isn't it? So those have opposite orientations. Since they have opposite orientations, okay, that means your only options are a single reflection. And a single reflection, get it from the pre-image to the image, or a glide reflection, a total of three. Remember, the glide reflection is a single reflection followed by a translation. Okay, a single reflection is not going to map P to A. P to A, the midpoint would be right there. Q to R, Q to B, that midpoint would be somewhere like this. Okay, so if I did that, that reflection would put it over here. So single reflection is not going to work. So therefore that one's out. So it's a glide reflection is what it has to be. Okay, so now, so that means it's going to take three. Remember, a single reflection followed by translation. So I go ahead and reflect this across the y-axis, reflect this across the y-axis, reflect this across the y-axis. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so then I go ahead and get that shape. Remember, it's congruent because all reflections are congruent. So now I have that, and then I go ahead and just translate it down. Remember, move it back here. Then I just translate this down the same distance, and then it lands right there. So a single reflection followed by a translation That actual word is called a glider flexion. DCAS doesn't use it because not all books teach glider flexion, but that's the technical name for it. And so on the DCAS, it'll say a combination of translations and reflections. So that was a single reflection and a translation. All right, that goes in, ends at 25 minutes.